Hello, everyone. I'm Guiltygyoza. I'm a co-founder of Topology, and today I'm here to talk about Shoshin. So the company was founded towards the end of 2021. We hypothesized that blockchain is a new medium to design a new kind of video games. And it's because it's a new kind of video games, it takes a lot of experimentation. So we've been looking for the Angry Birds moment for fully on-chain games since the genesis of the company in 2021. We've done some prehistoric experiments. So October 2021, we ran physics simulation on Starknet. These are numerical simulations that can compute the dynamics of physics systems over time. We also did some very primitive AI experiments. So on the right of the screen, that was a two-layer deep neural network fully represented in Cairo 0 smart contract that was able to run inference on the MNIST dataset. Test accuracy was only 94% because it's a small deep neural network. But nevertheless, we thought it was a lot of fun putting deep neural networks on a blockchain. And then fast forward to roughly April 2022, we conceived of Shoshin. So it is like 0x Monaco, but for fighting game, and there's no programming required. For those of you who may have not came across Monaco, 0x Monaco. It was a fully on-chain game by Paradigm where you submit Solidity bytecode that basically represents the strategy in a racing car game. So we created this asynchronous on-chain game that has the fighting game loop, and we wanted to make it so that the game can be playable by players that have never programmed a computer in their life. So the game idea is that player will create strategies, and the strategies will be put inside a 2D box that will fight 1v1. And once you create the strategies and submit the strategy, your hands are off the keyboard. We spent roughly a week writing Cairo 0 smart contracts as a proof of concept for Shoshin, and this was roughly June 2022. So what you're seeing here is we reused Q's art assets from the King of Fighter games to represent the fighting characters. And we have the Cairo 0 smart contract set up so that every single frame, our contract computes what each strategy decides on the action. The action would drive the animation state of the characters. The animation state of the characters would then translate to hitboxes by the physical hitboxes and the active hitboxes if they were actively attacking or defending. These hitboxes would go into a physics simulation that runs fully in the Cairo VM. We did very simplistic physics simulation. This was first order physics using fixed point arithmetic. And then a bunch of other things happened. Fast forward to January 2023, we decided to pick Shoshin back up and give it a fair run. So we fleshed out the smart contracts more. We built a web app front end to visualize the fights. So what you're seeing here is the really early days of Shoshin front end rendering layer, which is fully in HTML. The characters are just div tags, and the hitboxes are rectangles. So the early days of Shoshin, we exposed the Shoshin computer to the players. What we mean by Shoshin computer is that strategies in the Cairo smart contracts really are represented as finite state machines, where the transition functions between the states are binary expression trees. And despite us wanting the players to not know how to program, in the early iterations, we exposed the entire Shoshin computer to the players. So players have to craft decision trees with if-else branches, and they have to craft expressions that serve as the conditions that the strategy will use to switch between different branches of the strategy. And this was obviously programming all over again. So we went on a long journey of trying to abstract this more and more so that players feel more comfortable despite not knowing how to program. And we ended up with this structure as of now. This structure was directly inspired by the Final Fantasy XII game, where the game has a system called the Gambit system. And the Gambit system basically is a strategy that is expressed in a linear form. So every layer is like a thought in your head. And a layer will have a condition and an action. So if the condition comes true, you perform that action. And so you can see here we have layer 2, 3, 4, 5. For example, we can take layer 4, for example. Layer 4's condition is if my opponent is knocked, and also if I am within 120 units from my opponents, then my action will be a mix-up, 50% upswing and the other 50% probability moving forward. So we have these abstractions that we think would boost player productivity by a ton. And there really is a mental model. I think Gil finished the talk early, so I will explain this slide a little bit more. So we have this mental model called the Kolmogorov complexity. And the Kolmogorov complexity is this thing in theoretical computer science that says, given a programming language, given a target output, the size of the minimal program you have to write to produce that output. Okay, so for example, given the target of, let's say, a binary sort algorithm, if you were to implement this algorithm in brainfuck, then you will be writing a long program and it's not really readable. But if you were given JavaScript, then the program would be really straightforward. So the JavaScript, sort of the Kolmogorov complexity of this problem, given JavaScript, the programming language, is really small. But the complexity is really high given the brainfuck language. So really the programming language here, the expressivity of the language matters a lot. And we want the Shoshin editor with which players describe the strategies of their fighting to have as low of a Kolmogorov complexity as possible. So that really is our objective. And although we've been using this sort of linearized system from Final Fantasy XII, we will continue be abstracting this interface more to have more expressivity. And just a slide on the technical overview of the game system. The physics really is a very simplistic sort of system. This is like 1980s sort of era video game physics, where we have fixed point arithmetic, because in Cairo, I think floating point is still very expensive. Fixed point is easy to do. 10 decimal points, I believe, is the precision that we run with. We have first order physics simulation, because in video games, unlike real physics experiments, you don't need that much precision. So we run first order physics, also known as the Euler method, where you take acceleration and you update velocity, and you take velocity, you update the position of all the hitboxes. We have a very simplistic two-step collision detection and resolution. So in any game physics, there needs to be collision detection and resolution if you want things to interact amongst each other. So for example, if one character runs into another character, what really is seen by the small contract is their hitbox overlapping. And our system, pretty simplistic, we approximate each character by a single rectangle. So for those of you who may have played modern fighting games, Street Fighter, Skullgirls, Guilty Gear, etc. They have a lot of rectangles approximating the shape of the body, but we are just prototyping this game for the first time, so we have a single rectangle approximating the shape of the characters. And if the character is like punching or slashing, we have another rectangle that represents the range of the attack or the range of the defense. And then so collision detection really is about detecting if these rectangles overlap, and if they overlap, we need a way to resolve conflict, because we don't want rigid bodies to be overlapping in a physics scene. They will always stay apart from each other. But unlike in this reality where rigid bodies are sort of repelled against each other because of electromagnetic forces or some more basic particles, in physics, in game physics, we need to write mathematical programs that can resolve by pushing the rectangles apart from each other so that they stay away from each other. So that was really implemented in Cairo 0. And on the agent side, every agent strategy is represented by finite state machine. And finite state machine is just this really straightforward mental model that we have. So finite state machine is, if I am in the neutral state and if my opponent is offending me, I go into angry state. And if I'm in the angry state, I would perform a kick or something. Then transition functions between these states are expressed by binary expression trees. We need a flexible way to represent these functions in our Cairo smart contract, because what we're really doing is we want players to submit strategies. And these strategies are programs that are being computed by our core engine, our computer. And so we need a way to represent these functions, and binary expression trees is our choice of representation. And finally, we have animation state, which is represented by finite state machine. This is the common sort of industry practice. If you've used Unity engine or Unreal Engine before, animation states are atom state machines, literally finite state machines. And finally, everything was implemented in Cairo 0 and still is to this date. So fast forward to July 2023, we ran a in-person playtest in Paris, where 25 players tried Shoshin. And this was only campaign mode. So campaign mode is where we give you opponents and you fight the opponents in completely deterministic manner. And throughout the playtest, we received requests for PvP or online PvP or on-chain PvP, because if you play fighting game before, all you really want to do is you want to finish the story or the campaigns or the tutorial as fast as possible, and you want to battle other players. You want to beat their ass. So we received this request and we fulfilled their wishes. This was August. We added online mode. Online mode is where you can submit your agent, which can go into fight with other people's agents, directly player against player. So then we run a tournament, because we have this hypothesis that fighting game is where agent battles agent. But we, strictly speaking, don't know if this game loop will work in a player-to-player format. And so we need to test it. So we ran the Shoshin tournament, the first ever tournament of Shoshin in Stanford, around the time of Stanford Blockchain Conference, which was only last week. The tournament was run on August 28th in AC Hotel Palo Alto, where the Starknet Hacker House was hosted. Okay, but there's one problem. So if agents are deterministic, you run a fight amongst them, it's completely deterministic. So there's one fight, and that's it. If you run the second fight, it looks exactly the same, because everything is deterministic. And that really isn't helpful for tournament, because you want to watch more dynamic outcome. There's drama of people coming back in the next fight and so on. With deterministic agent, you really can't have that dynamism. And so we added mix-ups. Mix-ups is where you play fighting game, you want to be unpredictable. Every time a situation happens, you want to do something, but maybe also something else, so that you're not really easily guessed by the other player. Okay, so without the mix-ups, if you do low kick, you always do low kick. But with the mix-up, you can specify the probability of actions in a single layer. So once you're in that layer, you can have two different outcomes depending on a random number sampled in the Cairo smart contracts. That was a pseudo-random number. And the number is sampled from a hash function. So really, it is a uniform distribution. You can say, I want to do 10% action A, 90% action B. And every time you go into that layer, the random number will get generated freshly, and you will do something randomly. And so with non-deterministic behavior, what we really can do in a tournament is we can have lives. So we can do best of 3, right? So this is 1v1, and we do rounds after rounds. Whoever wins 2 rounds first wins the entire game. And because our agents are non-deterministic, there's randomness. Every fight looks slightly different, and there's opportunity for comebacks, which is great for generating drama. Okay, so tournament structure, simply speaking, it's a double elimination bracket. Players fight amongst each other in a best of 3 format. In between the game, you can resubmit your agent, because if you lose to an agent, you see patterns of other agents' behavior. You can resubmit your mind with tweaks so that you may come back with a better behavior later. And the results was pretty cool and pretty surprising to us. There were nail-biting comebacks. which means that you have players that went to the losing brackets and went all the way back up to semifinals, which is amazing. And it was really time efficient because we were able to run double elimination brackets, best of 3 fights with non-determinism, 15 matches less than an hour. And underdogs emerge, which means that there are strategies that look very inferior to most other strategies, but they happen to beat the dominant strategies that happen to overpower all the other strategies. So there was a lot of this dynamism, which is really cool. And the dominating performances was this is the championship fight between Jack and Beha. The fights were coming back and forth. Best of 3 rounds, where the first round was, I believe, Jack won the fight. The second round was Beha winning the fight. And so it comes down to the round 3. And this was only possible because there's non-determinism. We have roughly 40 players attending the tournament, 13 players competing for a championship. And we make them rocks, basically trophies in the form of rocks for the number 1 and number 2 players. And it was a lot of joy for players watching their agents performing fights like a cinema on a big screen. And players were really proud of their achievements. So that was really cool, them tweeting about the tournament experience. So lastly, I want to talk a little bit about what does all this mean for Starknet. This screen encapsulates a lot of our experiments at Topology since the genesis of the company. On the top left, you can see Isaac, which is a 3-body problem physics simulation in the Cairo smart contract. On the bottom left is the login screen of Shoshin. On bottom right is the Mumu, which is another experiment we did about digital alchemy and sort of this pipeline of emojis transforming into other emojis as a fully on-chain simulation game. We think that Starknet gives you verifiable compute via validity proof. And with all these sort of compute surplus in the blockchain space, it's interesting to find good uses for those verifiable compute. And we think that interactive storytelling, interactive entertainment simulations is a really good way to transform those verifiable compute into new kinds of experiences. And so that's why we've been running all these experiments, and we hope to find new paradigms and new applications that could be possible on the blockchain. So for those of you who are gamers, go play Shoshin at shoshin.gg. And those of you who are not gamers, you can follow along our journey on Shoshin_GG on Twitter. Thank you, everyone, and welcome questions. Yeah.
Is this the trick that kind of like the players submit their strategy on beforehand, and then because the L2 block is like newly generated, and then like block cache is totally random as a like future. So because of this time gap, you can get the randomness very fresh and non-deterministic or known by someone else from like beforehand. Like, am I understanding correctly?
I think half and half. Our entire Shoshin game loop runs in a single transaction.
Okay.
So it's a single block interaction with Starknet.
Then how then you generate the randomness? Because as far as I know, like Starknet don't have a randomness in the native. So
right. So our randomness really can be understood as game randomness. You know, when you play video games, there's something called seed. And when you're given a seed, you have all these outcomes. If you change the seed, you change the outcome. But if you use the same seed, you'll get the exact same outcome. It's pseudo-randomness that is a function of seed. And if you don't throw in any other sources of entropy, then the same seed will give you the same outcome, which is great because we can reproduce fights if you remember the seed. So given the same two agents, we can say seed 77 gave us a lot of amazing fight. Seed 11 was like a 2-0 fight, less drama, and so on and so forth.
Yeah. Oh, okay.
And then, so it comes down to choosing the seed, right? That is sort of fair to both players. But this is really another layer of a game loop on top of the Shoshin game loop. It's about choosing the seed, and there's like attack and defense. And so we want to push out a on-chain PvP protocol in the next 2 months, hopefully, where so if I can attack you, and rationally speaking, I will choose a seed that optimizes my chance of winning. But there can be a path of view, basically rebuttal, and you can choose a seed that works for you best, and that concludes the fight. So we don't really need, maybe in DeFi protocol, true randomness. We just need randomness that makes sense in a game setup.
Okay, understand. Thank you.
Why did you guys build this in Cairo? What unique feature of Cairo that makes it very suitable for building this game?
So this game was built in the Cairo 0 era, and I think we came across Cairo as this very low-level programming language that is low-level than Solidity, but it's higher level than Circom, which is the other dominant language for writing zero-knowledge circuits. Circom wasn't really productive if you want to write big game loops. Cairo was low-level enough so that we understand what everything is going on in the VM, and it's just that our internal team developers didn't really like Solidity as a programming language, and so we chose Cairo. I do think that the entire Shoshin game loop, if we want, can be reproduced in Solidity. But it's just that we think that the EVM space has a lot of interest and stake involved. And so the innovation is kind of complicated. But in the Cairo space, things move around more freely because it's a newer ecosystem. So we get to screw around a lot more and do weird stuff. I think that's primarily the reason why we chose Cairo, not out of sort of technical superiority. But of course, if you're in the Starknet ecosystem, there's this concept of fractal scaling and recursive proof. All of that gives us more confidence that we can run more complicated Shoshin, so that we can run Shoshin fights off-chain, and you can recurse the proving so that you're rolling the proofs and you send the proofs on-chain for verification. That allows you to run longer fights among more complex strategies.
And also that now Cairo 0 will soon be deprecated. I guess we'll be migrating to Cairo 1.
Yeah, so we have been troubled by this a lot. It was only because our bottleneck really is on the front-end side, where we want to improve the editor interface, the Kolmogorov complexity thing. But we are aware that Cairo 0 will be outphased. And we decided that instead of a rewrite, which is a little bit boring because keeping the same feature set but re-implement it in a new programming language feels like work. So if we're going to write a new game in Cairo 1, we'll just write a new game. So I think the current idea is we take Shoshin, we slap an on-chain PvP protocol on top, and we call it Shoshin. And we will move on to Cairo 1, fresh front end, and make a new game. In terms of what the new game look like, we don't know.
Oh yeah, and one more. Would it be possible if you built this using something like Dojo, for example?
Well, I think nothing is impossible. I think that what will likely happen is that we will study the Dojo code base. Primarily, I think how you abstract the ECS pattern and how you do code generation. And whether or not we will use Dojo is, I think, undecided. But I think we'll be heavily inspired by your pattern. I think that's the likely outcome. Okay, if there's no question, thank you, everyone.